basically continuing what I've done in the couple of conference before. It's about kind of interesting mathematical problem solving. So if you look at the link, the download the link in the subscription in the description, you will see actually we almost have like 6 problems included. So I won't be able to cover everything today, but I have a office hour on Friday. So there will be a whole hour on Friday, so we can go through all the questions you still have for the notebook, and maybe some of the leftover problems we do not cover today. So make sure you stay tuned, and I will explain to you all the interesting method and algorithms that I included in those notebooks to solve these kind of interesting problems. Okay, so first, usually I start with a very interesting geometrical problems. It's a pre-college selection problem from Peking University, which is one of the top university in China. So they do something like different from the SAT and the college entrance examination. They sometimes put extra round of test to select the best students in the country. So one of the problem is about geometry is quite interesting. So given a triangle ABC and point D is on the segment BC. So say you put a triangle ABC, draw 3 points, and the D is a point on BC, and AD is angular bisector of angle BAC. And then the incenter of the small triangle, the ADC, coincides with the circumcenter of ABC, which is basically the center for the the circle that in which triangle ABC inscribed. And then we are asked to find the value of angle ACB. So this is some of the, I think, problem is very hard if you want to just draw with compass and a straight edge or with like GeoGebra, you know. So because some of the constraint is quite implicit, so you need I mean, it's easy to draw triangle ABC, and it's easy to draw a angular bisector for some angle, you know. But it is really hard to set up the right triangle so that the incenter of the small triangle exactly match the point of ABC. So I think this is a type of a problem very useful. You can see the Wolfram language, the geometric scene and the geometric solve are really, really useful in this case, because the syntax here is basically like setting up a set of equations. So in our case, we can just sit A at origin and B at some predefined coordinate on x-axis. Because in this case, you can see that it's really, it's just ask you the angle. So really the size of the triangle doesn't matter. You know, if you some smaller triangle satisfy this condition and the larger one can be zoomed out. So in this case, you usually don't worry too much about the exact length of the sides, but what is important is the relative size. For example, if you set up AB and then probably AC and CB are determined, you know, but it's really not determined by the position of the triangle in the space. So in this case, I can just put a AB as like predetermined or the known variables. And seems because we are looking for the ACB, so C is kind of unknown. And the D and O is D is basically the point D on BC, and O is the circumcenter of ABC. So in the setup, what we need is triangle ABC, and then we need is a triangle construct. Triangle construct is a very useful function if you want construct like a subtriangle or incenter or circumcenter, excenter, all kind of properties of a triangle. So for example, here D is the angular, AD is angular bisector. So here is angular bisecting, it's angular bisector. And the Cevian endpoint means I'm interested in the location of D. So on the side of BC. And O is the triangle constructor, it's the incenter, which is the same as the triangle constructor circumcenter. So you can see that basically this is simple English. And we are putting effort to maybe automatically using like LLM to transfer some of the language, the statement of problem into this type of thing in the future. But if you even do that manually, you can see it's really not that difficult. You know, it's basically just if you learn about the basic syntax, the construction of this geometric scene is quite straightforward. And then if you want to plot that, there's a function called a random scene, random instance. It's basically set up some random points and to wiggle around to see if we can find a solution for this construction. And it turns out it can directly find this construction, but it takes a little bit of time. So I just pre-cache the result here. So if you run this random instance a couple of times, you will find that it always shows the same triangle. The only difference is sometimes the C will go to below the AB. So it's like a reflection of this point of C with respect to the line AB. So you only have two cases. So which means if you have this set up, looks quite random, you know, but it actually determines uniquely a triangle that I mean, only one type of triangle that satisfies this kind of condition. And the geometric solve actually will find it for you. If you click the control and there's find conjectures, it's actually with computer stuff. So that you can choose a couple of conclusions here. So this is also one of the quite interesting. It shows like CAB, the larger triangle, is similar to the smaller one. This is one of them. But we are looking for the angle. The angle is ACD equal to BAD equal to CAD is 36 degrees, which is actually give us a symbolic solution for that. So this is very interesting because you think about it. O is the circumcenter. So it is it must be on the perpendicular bisector of segment AB. And also O is the incenter for ADC. So OC must be the angular bisector for ACB. So this guarantees that ABC must be an isosceles triangle. So in this case, this is this configuration and the value of the angle actually makes sense. It's not something randomly generated. It really shows the configuration is correct. And then we can just quickly go through the proof. And okay, if you don't want the scene, you can just inject the geometric scene inside the geometric solve values. It's basically the same thing, but you can specify which value you want. For example, I want a ACB. And it turns out for a pure symbolic computation, it takes quite a long time, like 38 seconds to find the value, which is pi over 5. But if you want something quicker, you can just inject the random scene we have already generated, which gives you a numerical value. And this numerical value happens to be pi over 5, and you only take the decimal form instead of symbolic form. So this is 0.62. So it's the same thing as this value here. So basically all the symbolic and numerical values agree to each other. So we were pretty sure this is a correct computation. And then we can take a look at the quick proof of this thing. So let's see. Let's assume ACO is X. this is I'm marked with a star. And then because it's a angular bisector, so this star is also, this part is also a star. So I just want to make sure that, I mean, it's a different star, but it's the same as X, you know. I just want to use different color to mark different angles, but this star means it's the same value as ACO, because it's angular bisector. And because O is the circumcenter, so OC must equal to OA. So OCA is a isosceles triangle. So you move this star to here. And because O is the incenter of ADC, so this angle reflect to this angle again, right? So DAC is 2x, they're basically 2 stars. And in the problem, it also says AD is angular bisector of CAB. So if this is 2x, then DAB is 2x. So in total, you have 2 plus 4 and 4x. So in total, you have 10x. So 1x is 18 degrees. So this is basically how you solve, and ACD is 2x, so it's 36. So this matches exactly what we have in the symbolic solvers. And you can also find some of the theorems we used as a like inscribed angle. You know, it basically shows how these angles move around each other. If you have to fix the endpoint of a chord, and you move the third one on the given circle, the angle will be the same. It's exactly half of that. So this is also something quite useful if you want to solve this type of problem on circle. And what was more important about using Wolfram language graph geometric scene here is you can sometimes manipulate the problems. It's not the manipulator function here, but you can actually create a different version of this problem. So in this case, you go back. It shows you D is on the segment BC, and AD is an angular bisector of BAC. So so basically, AD is like dividing the angles. But what if D is something different? You know, like AD is a height, or D is a foot. D is a foot, right? So basically, AD is perpendicular to BC instead of bisecting the angles. So I think this is something really good about the language design. All you need is just change this part. So in this case, you scroll down. We only change the property for D from angular bisector Savian endpoint to foot. That's everything is the same. And then you use the same geometric scene and the random instance for the second scene here. And it gives you this construction. And this triangle is also quite interesting. It's also uniquely determined by this O here. You can just use almost a similar argument we have before. So assume one point here is X. And you have 4x here, right? Because this is also a right triangle, because all the base 2 other angles are the same. So the only option is ADC is a isosceles right triangle. So the only option for angle ACB or ACD is 45 degrees. So this is basically shows us the result. So X is 22.5, and the 2X is basically 45 degrees. So this is something quite interesting. You can also play around with the point D to see other properties. If the same coincidence of 2 centers still keeps. So this is something like I feel it's quite interesting in geometric scene. You know, typically for this type of implicit requirement, and more about like equation solving type of problem solving. So this is will be more useful than the I call it the CAD type, the CAD, like you draw the lines by itself. Things will be more useful because this requirement is quite hard to draw if you only have A, B. Now you need to manipulate not only the location of C on the circle, but you also need to find the right radius for that, which is something we actually need to solve for. So, okay, so this is the things I have for these geometric problems. And if you have questions, you can leave it in Q&A session. Then I move to the second one. The second one is quite interesting. This is a problem selected from HMT November 2023. So if you look at the grid of clocks, it probably reminds you of some Hitchcock movie about murders in Lock the Door. Usually they find someone dead on the ground, everything's locked, windows locked, and usually the first thing the detective notice is the clock on the wall. So usually the clock, the time of death or something, it is very important. And if the murderer is smart enough, they usually manipulate the clock on the wall to confuse the detector. So usually this type of a clock thing is always amazed me. So, and I happen to see this problem. I think, wow, well, if I can visualize the solutions in a very cute style of the clocks, it'd be quite interesting. And this is definitely something you can print on a T-shirt. I really like the visualization here. So if you look at the clock here, it indeed looks like a random at the beginning, but if you look closely, you will see some interesting patterns. So in all the clocks, one of the hand is an angular bisector of the angle formed by two other hands. So it's basically almost the same problem we had before. It's about angular bisectors. So sometimes our hand is the angular bisectors. Sometimes the minute hand or its extension on the opposite side is the angular bisector. Or we can see it's angular bisector of the sort of a complementary angle. This angular bisector basically outside of the angle. But if you elongated it this way, you can see it actually divided the angles in the same portion. The same as this. In this case, the second hand is the angular bisector of the two hands. Okay, so the question asks you between midnight to midnight, basically 24 hours, how many times such configuration will show up? And excluding the midnight, like 12 o'clock, and also exclude sometimes if two hands overlap. We are talking about a mathematical overlap, because in physical world, the hand got some thickness. It always overlaps at the same time, but that's not what we consider. We are talking about if you assume all the hands are a perfect straight line with a zero width. So how many times they overlap? This is a algebra plus a little bit simple number theory stuff. So at the beginning, it seems really random, but actually there is a close to 6,000 times this will happen every day. So let's see how we approach the solutions. So in the official solution, it gives a quite good setup. So instead of just work on the minutes or seconds, by the way, here's another thing we need to make sure is the second moves smoothly. It's not a quartz, like stepwise. So if you can see some of the time, it's the second is like between the marks. So it means it happens in the fraction of seconds, which is not possible for a quartz clock. So the hand must be moved like smoothly. So in this setup, I use a variable t. The t is between 0 to 2, which means it counts the number of full revolution of our hand. So 0 means at the beginning, and the 2 means after the hour hand make 2 rounds. That's the other midnight. All right. So in this case, we are using the number of full revolution of our hands as a variable, and then in this case, we can easily see that we need to talk about the 3 cases. So what kind of 3 cases is if a hand divides the angle formed by the other 2 hands, you have 3 options. Sometimes you think maybe like 6, but 3 is enough. Think about it. So 2, 3, 4, it forms a kind of arithmetic progression. So 3 minus 2 equal to 4 minus 2. 3 minus 2 equal to 4 minus 3. So what makes the setup slightly easier than making like 6 different cases is you only need to choose which one is in the middle. So in this case, you can see that if we fix the which hand is the angular bisector, we kind of don't need to worry about the order of the other 2 hands, because they are going to be handled in our algebraic equation here. So let's see. The angular displacement for the hour hand is basically mod T1. It basically says if t is 1.2, because the face is only have like 12th grid. So basically you only choose the fractional part, which is the same as mod 1. And the minute hand is 12 times t. So because the minute hand moves 12 times faster than the hour hand, and same thing applies to the second hand, which is 720 times faster than the hour hand. So you can see it because during 1 hour, during 1 day, it runs like 12 times 60 rounds. So for 12 hours, it runs 720 rounds. So that's why you need to times 720 times the number of revolutions of hour hand. So if let's say, for example, if the hour hand is in the middle, so which means it is the average of the angular displacement of the minute hand and the second hand. So basically, it's a plus b over 2 equal to c. So this is in this case, it's like a plus c divided by 2 equal to b. And if this is the second hand is in the middle, so it is a plus b over 2 a plus b divided by 2 equal to 3. So basically, you set up 3 type of equations. So this is like choose 2 divided by 2 equal to 1, or basically it's the 2 end add up equal to twice the middle. So this is basically the solution. And this also uses algebraic effect of mod, is mod a m plus mod b m equal to mod a plus b m. So you can just thread everything into the same location in the mod function. It'll basically solve for you. So this in this case, this is like the hour hand is in the middle, right? And you just solve it from t to 0 and 2, and exclude the 2 and exclude the 1, because at 1 it's basically you are at the noon, 12 o'clock at noon. So all the 3 hands like overlap altogether, so it must be excluded. And at 2, it is excluded. And the positive reals here exclude t equal to 0. So basically, you run this function and it solves the t in this case when the hour hand is in the middle. And you do that 3 times. This is the first time, the second time is the minute hand in the middle, and the third time is second hand in the middle. So now you have like all the solutions. And because when the our hand is the middle, is exclusively I mean, in this case, it's disjoint with this event. And same thing happened here. So all the three events are disjoint. So you can add up everything together. So it basically shows the solution for this setup. But it's not enough. We need to remove some cases, because in this case we ask that no two hands overlap. So we need to find out when two hands overlap. So in Wolfram language, you basically do that in brute force. So this basically gives you equation that two hands overlap. Two hands overlap is very simple. Recall that these are the three equations for the hand movement. So if two hands overlap, so basically it means like, so for example, if hour and the minute hand overlap, so it simply means the difference between these two are 0, right? So it's mod 12 minus 1, it's 0. And the same thing for second and hour hand. So you minus second and minute hand, it's 720 minus 12, 720 minus 12. So same thing applies to the second hand and hour hand overlap. So in case you have you can run this thing, and the result is quite simple. It's half and 3/2. So for half turn, it's basically 6 a.m. 6 a.m. and 3/2 is 6 p.m. So if you have like a analog clock with you, you can easily see that that's correct, because at the 6 o'clock, the hour hand points downward, and both minute and second hands point upward. So they are the only overlaps things here, right? But if you want to do that more mathematically, you can do this thing. So you see, if t is some like valid time, it must satisfy one of the equations we have so far, because if you 730 means it is t times 730 is like integer, right? And t times 697 is integer, and the t times 1027 is integer. So basically, it must satisfy one of the equations. And if two hands are overlap, it must be one of these equations. So basically, we pair up this 720, 730 with all these numbers here, like 7, 708, 11, and 719. So you basically see if they have any common divisor larger than 1. So basically it's do co-prime test. So if they are not co-prime, that means there's some divisor will show up. So the divisor, when divisor shows up, it means we have some sort of like a two hands overlap thing, and it must be excluded. And you can see that 730 and 708 has a greatest divisor 2, which is exactly the denominator here. So once you have like anything GCD more than 1, the fraction corresponding to that denominator in the solution will be the case that two hands overlap. And unfortunately, we only have one of them, and it's only 2. So we are pretty sure that we exclude only 2 points from the joint, the union of all the solutions we have for each cases. Now what we can do is just to find the complement of the union of the solutions and the two values that we don't want. And 4700 minus 2 is 4700. 4702 minus 2 is 4700. And this, finally, we have a simple function that shows you the how I visualize recover the solution, recover the hand position of the hands from the solutions we have above. So this is a very nice one. I put a like random choice over here. So if you run that a couple times, you will see different construction. So these are not predefined, but just randomly choose those solutions and visualize the clocks. So I think it's very, very nice. Typically with the gauge style, the pastel, I think the diagram looks easy to understand, but also intriguing if you don't see what's the pattern behind it at first time. So this is something I feel because elementary math and algebra and slight number theory matches very well with graphic design. So I hope you enjoy it. Okay, so I think it's time for today. So if we can move to talk about the rest of the problems in the office hour, and you can leave questions about today's talk, and I can answer you. Can you? Oh, okay. So here's a Q&A. Can you derive a geometric scene from an image? So currently we are exploring the opportunities to do more about it, image processing and extract the the points. But currently, in the current version, we do not have a solution for that. Okay, I think that's it, and I will see you on Friday, 1 p.m. and discuss more about the number theory problems and some of the combinatorics problem I've prepared. So hopefully you spend some time to read those scripts, and once we go through all the solutions, you will be more prepared. And because I feel some of the problems are quite tricky, so it's really will do no bad for you if you prepared a little bit. All right, thank you.